Hello and welcome to Chapter 4. In Chapter 4, we're going to discuss leveling. Leveling is very important. If you think about construction, we want to know that water drains appropriately, whether it's too fast or too slow can cause a problem, and you need to figure that out with a level. The other thing is we want buildings to be level. We want floors to be level. We don't want to open up a door and roll down the floorway or hallway or something, or drop a ball on the floor and have it roll away from you. You don't want any of those things to happen. So using a level to keep things at the same elevation is very important. You would do that with a hand level at your house, something people might call a spirit level, to make sure a picture frame is straight or hung straight, or a mirror is hung straight, those type of things. But surveyors use a level to get elevations, differences in elevations to measure with. And in construction management, this is the one thing that you can do in the construction management industry, usually like a field engineer, project engineer. That person can actually go out with the right equipment, which is relatively inexpensive, and check a surveyor's work, check various measurements that we're going to see for quantities. It's a lot of things that you can do if you know how to operate a level. So that in mind, let's go ahead and start with the slideshow, PowerPoint presentation for Chapter 4. And I think you'll find this hopefully very interesting. And I definitely want you to go and look at the video that I posted on leveling. It shows you exactly what you're doing and how to see things and how to use an automatic level. That's what the guy is using there, an automatic level in that video. So let me share the screen here. Alrighty. Chapter 4, leveling. In this chapter, you're going to see these general terms. I went too far as usual. So an elevation is the number of something is above a datum line. And the datum line, as you see at the bottom, once meant mean sea level. Everything was once measured from mean sea level. It doesn't have to be. The elevations can be assumed. A lot of times on construction sites, we would have an elevation, a benchmark for the site that was assumed someplace, and a nail driven into a telephone pole or something like that that was never going to move, and everyone coming to that construction site would know that they could use that for an elevation, but it was actually something that was often assumed. A vertical line is a line measured from a point above the surface of the earth toward the surface of, or to the surface of the earth in a direction toward the center of the earth. And we'll see that here in a moment. A level line is literally just what it says, the line that is level between 2 points, A and B. The top of that picture frame is your level line. Horizontal line is a little bit different than level line, and we'll see that in a minute, but they're really pretty similar. And we talked about mean sea level as once being the standard for which everything was measured from. However, I do remember people running, you think that water is at the same level all across the world. The oceans would be at the same level. That's not necessarily true. Various reasons why, I'm not going to get into them for this class, but I do remember sometime in the 80s, the federal government ran trigonometric and actual levels with a level gun like we're looking at, or going to look at. And they ran from the Atlantic Ocean to the Pacific Ocean, and they were not higher, or they were not level. Everything they did to check in between, they were not level. So mean sea level is something we've gotten away from a little bit now. I can tell you like something, you know, like in the Chesapeake Bay, let's say, the elevation of the low tide and high tide are not zero. Generally around here, high tide is 1.2, 1.4 feet. Whether you're on sometimes it gets as high as like 1.8 feet. And that is whether or not it's on the Chesapeake, the Potomac, or the Patuxent, or anything that's a tributary of any of those. It's tidal. High tides are about that. Low tides are something just under a foot. 0.6, 0.8 feet, something like that tends to be what low tide is. So we see that mean sea level is not something that you look at anymore or use very often, but it has its benefits, and there are times where we want to get a measurement on the mean high water so we have a good idea of what elevation we're at. This is the idea of leveling. This is, as it says, leveling concepts. So keep in mind we have the ground surface that does this. We've got an earth that is, in theory, relatively round, and in theory is perfectly round. We know it's not truly round. So what we have here is a level line where the datum, they show mean sea level as being 0 feet. That datum line has an elevation of, say, let's just say that's like 100 feet. Well, that 100 feet above it, all the way around, is going to be the level line. And here, for example, is just a B, a higher level. And there's your difference. So oftentimes we want to find this measurement right here, the difference between an A and a B as their level. Next slide. Here's a little bit different picture, but it's the process involved, and it's going to point you to something. Notice that the earth is curved, but yet we're going to say that this is a level line right through here, and then we're going to be able to utilize this to get our information. And we're going to explain that. There's some things going on that don't make this an actual level reading. And there's ways to accommodate that, and we're going to see that here in a little bit. But this is the idea. You have a point, say right here, that you know the elevation of, and you want to find out the difference from here to here. And this elevation, it says, is 61.27 feet. You stick a level gun in the middle, you set it up properly like the video showed you, and you take a reading over here. This reading is 6.27. So we are 6.27 feet higher than this elevation. Then that right there, so 61.27 plus 6.27 equals this elevation right there at the line of sight. When you turn and you look at this one, you see 4.69, you subtract that, and now you know the elevation at B. So while that might look a little complicated, that's what we're doing all the time when we utilize a level gun or an automatic level and a stadia rod, or some people call them a grade rod. That's what we're doing constantly. We're coming off of a known elevation, establishing the elevation of where we are, and then transferring it and lowering it to a new position. That is the process of leveling. Horizontally, we're like tangent to the earth. And so this amount right here is also what you'd be looking at for distances. The further away you are, the further this level line and horizontal line get apart. You can picture if you were to look for miles and miles away, level is going to be down here and horizontal is going to be up high, and you're going to be pretty far apart right there. So it's something that you have to be mindful of, is that the earth is curved. And so we can't actually measure on a curve very well. So how do we account for that? Well, it's coming up. curvature and refraction. Curvature is the curvature in the earth. Refraction may sound silly, but it's light bending off the Earth's atmosphere. So I want to think that in 1 mile, there is like 8/10. You would see 8/10 of a foot high in 1 mile because of curvature. But then that comes down 1/10 of a foot because of refraction, the light bouncing off the atmosphere. I want to think the number is something like that, about 0.7 or 3/4 of a foot, and 1 mile is you'll be looking higher based upon curvature and refraction of the earth, or curvature of the earth and refraction of light. So you have to take into account and so why you do this is you keep very short distances on construction. It really has no effect. If you're trying to go long distances, you have to keep the back sight and the foresight, the two distances, equal or close to equal, and you will eliminate the effects of curvature and refraction on your readings. This is just a table here for curvature and refraction. I was actually wrong. So in 1 mile, you're looking at, it says 0.57 feet high in 1 mile. So you can see here in 300 feet, you're only a couple hundredths of a foot high. In 1 mile, we are almost 7 inches high. I said 7/10 of a foot. It's actually 7 inches high. So that's what you need to know about curvature and refraction. Just remember, keep where you're coming from and where you're going just about equal, and you don't have to worry about it. These are the types of levels that are used now. Tilting, I don't see many people using a tilting level. You can use a total station today, and that would accomplish the purpose or effect of a tilting level. But if you had a total station, you probably wouldn't use a level rod with it. Digital levels are a little bit expensive, but they're very good. They're also a type of digital level that is not that expensive. There's digital levels for Surveyor that read automatically and are expensive and very accurate. There's a digital level that's used along right here with the rotary laser, very similar technology, where the laser will spin around in the middle of a construction site and you read digitally on the rod. It has like a digital reading, or it has a sound that makes a beeping sound when you are at the right height. Surveyors generally use this right here, the automatic level. And that automatic level is the one that's in the video that I got for you. What it does is it has this ability here. It's got like magnets in it and explains this whole thing. I don't need to go over it. But what will happen is you press a button on the side of it, and it automatically releases everything inside, and it becomes level, and you can take your reading. So you set it up just like the guy did in the video. You get everything close, but then when you press the button on the side of it to get the automatic level, when you're looking through it, you see the whole screen shake a little bit, wiggle, and then at that point when it stops, you're truly looking level through the instrument. This right here, I have a video that I got also for you that I really want you to read. But this is reading the different faces of the rod. There's a whole exercise on that in the book. There's questions I've asked you about it. And it's very important that you understand how to read a stadia rod. You can use anything for a stadia rod, but most of the stadia rods that you would see on construction sites are fiberglass with numbers on it just like this. I have used a carpenter's measuring tape. At my house, you know, you want to build, I built a shed, I built a big deck, and I've used a carpenter's tape and my survey instrument to look through it and use the same purpose as the stadia rods. I am not going to go through how to read in this video because, or this lecture, how to read these, because the video that I got for you does an excellent job in telling you how to read it. It does a better job than the book, and I really suggest that you would look at that and watch it and take from it, because this is the one thing that if we were in person, I would have you physically doing and computing, and we would be checking elevations across the parking lot and check how the level and distance from, say, the doorway of the building out to the parking lot. We would do a lot of things with it that are very practical. So this is something you really need to look at, is how to read these rods. Let's see, once more, too far. All right, some abbreviations that you need to understand, and a couple of them, and they're mainly for note-taking, except for this one, the benchmark. The benchmark is the elevation of at a particular point that controls an entire construction site. Like, what is your benchmark? Where did you set a benchmark? What is the elevation on the benchmark? It could be a rim on a manhole. It could be the corner of a storm drain, the top of a fire hydrant, or a lot of times we would take a large nail, a really large nail, like a spike, and drive it into a telephone pole. And that would be our elevation. That's what we would work with. So that's very important, is to understand that a BM is a benchmark. Temporary benchmarks doesn't come into play much, except for in the book and some note-taking exercises. A turning point is the elevation at the instrument, and we're going to see that in a minute, where you're moving from a known elevation and you're skipping it further ahead in the process of measuring, and until you get to the next point that you want to be a benchmark. The height of the instrument is just what it says. It's the actual height of the level instrument that you're looking through, your eye height. FS is foresight. Intermediate sight, you won't see too much. The book has things in it that we just don't use much of anymore. Here is the practical example of exactly what you want to do. You want to transfer an elevation from BMA. It's known right here what this value is. You set up in the middle. See, you're roughly in the middle, so that eliminates curvature and refraction. You get a reading here. And so this elevation here is going to be 410.26 plus 4.71, and that's what you're going to equal. You turn, you take another reading over here. It says 2.8. You subtract 2.8 from 414.97, and you would have the elevation at B. It's as simple as that. But yet, leveling is something that's very important and something that you need to be able to do as a construction manager, construction setup, or construction project managers on construction sites. So here's the actual note-taking in the process. It's a little bit of the note-taking. I wouldn't take notes like this, but here's the math behind the process. Keep in mind that coming from a benchmark, coming from a known elevation is always a plus. And then going to an unknown elevation is always a minus. Plus, we come up, minus, we go down. We set a point here called the TP, or the turning point. We then take our level rod uphill, or level, we take it up the mountainside. We get another reading here, and then we turn and we get another one down here. And now we can set a new benchmark elevation over here. So this is, again, something done very regularly in the construction industry. And that's the practical procedures for it. Here's what I told you before. This is the simple field notes. I told you the back sight was plus, you're going up. HI, you need to know the height of the instrument, where you are level. That's the key to all of this. And then FS is a negative symbol, so that we're going back down. And you'll need to know how to decipher and reduce the field notes as part of this chapter. This is not that important for us. It's not very important for construction surveyors either, or construction management, but there is a set of rules as to how accurate level loops and level work is to be. So, but many people just don't do that type of work anymore. This is a situation here where you're getting shots along a baseline. What do they give us here for some text? Yes, example of profile leveling or along a baseline. You get a profile along a baseline. And the way you would do this is you have to know this distance along the baseline itself. And you got to know where you are to be able to get these shots and know the distance. There is a way to do it with a stadia rod. We're going to see that here toward the end. But essentially, this is what you're doing. You're taking this known elevation at a benchmark. You come up, you get the elevation of the instrument, the HI, which is the elevation of being truly level through the instrument. And then all of these are negatives. We have a negative 2.06 to get the elevation right here, a negative 1.17 for this elevation. And then you go through the whole process, and over here in theory, you would check to an elevation that's known. You would end on BM 461 with a known elevation that you would want to know how good you did. But this is a way of getting the profiles and the elevations along a road or any other sort of baseline, maybe through a parking lot, something like that. Or water line. Water lines and sewer lines are laid out with stations like that as well. Here's your typical field notes. Let me zoom in just a little. Again, you have that plus symbol when you come off the benchmark. This is where your elevation is. These are the negative shots over here. The IS is the intermediate shot. We don't really use that too much. Everything here would be really a FS on this side. And you would get to a turning point. And what I would do in my field notes would be I would put this 0.982 right here. And then the next thing I would do is come over here with the I'd fill in this information right here, that'd be on this line, but this one right here would be down one. And all of this would be shifted down one space is how I personally would keep the notes. There's nothing wrong with this way. I just don't want to put a backsite and a foresight on the same line anywhere. So somebody reducing it and figuring out these numbers might make a mistake. If I keep my shots separate on different lines, they won't make that mistake. But there's nothing wrong with how the book is telling you to keep track of these notes. Same thing that we're looking at here. This is called a cross section. Notice there's no profile. There's no stations here. So this would be like, this is the center line of a road. And you want to know like how far, like this, at every interval of say 50 feet or 25 feet, you would get these shots. And then you would start to see a cross section like this. The reason that this is good is for quantities of material, how much dirt needs to be moved, how much dirt needs to be brought in. That's what you do that. That's the very purpose behind this type of work, a cross section for surveying. Here's the notes. They're very similar to the profile notes. Very, very similar, except that here you're giving distances. You have a station and you're saying 10 meters left, 2.7 meters left. Here's the center line elevation. And then there's how far it is right for 2 shots. That's what you're doing so that somebody can plot the cross sections. Here we are again with this line of sight and all. The book explains this kind of well. It's called a peg test. It's in figure 4.23 of your book, and starts up right underneath it. And what a peg test does is it tells you if your instrument is out and by how much. If you want to know how far this thing is out of whack, what you do, and the book explains this, but I'm going to tell you because it's kind of important. You want to be able to look through this horizontal line and figure out that you're truly level. But if something's wrong with your instrument, there's going to be error. You're going to be looking high or low from where you really should be looking at. So what you do is you set 2 points here that are pretty far apart, 200 or 300 feet apart. And then you set up in the middle. You can just, again, you can pace there. It's one of the functions of pacing. You could do this whole exercise by pacing and just keeping yourself in the middle. You could go 100 steps, and then you keep this at the 50-step mark. Set 2 points on the ground. Take a reading over this one and get that answer. And then take a reading over here and get this answer. There's error that's in here. When you then come over here and now you move from this one down here next to the first shot you took on A, you get close. This distance here might be 4 or 5 feet. That's all you need. Maybe if you get closer, fine. You take a shot right here and you get a distance of like 4 or 5 feet. The amount of error in the gun is negligible at this point. It's too close for you to worry about it. When you turn now to look over here, whatever your error is going to be doubled. And this is the true error of your instrument, is half of this distance right there. So you should be, this is a situation where you need to know what these elevations should be, A and B. Would be helpful, but otherwise you'll have a different answer. You should be seeing like this, whatever this number here is the same here, and you get twice the error. I have done this once or twice. The level guns we use that are automatic levels tend not to be much of a problem, and you don't need to do this very often. The laser levels, never have to use them with the laser level. So, but it's a technique to understand what you have and to fix some error. Now, this is a lost art. If you can do this in the construction industry, you are going to be extremely valuable. This is stadia hair reading, and it's done for getting a distance. So if we go back and we look at the rod, let me show you a rod. Might have been one coming up, but I'm going to go back. When I show you the rod here, whoops, you have these distances, these marks. So 1 foot, 2 feet, and then tenths of a foot in between. So that's going to become important here in just a second when we look at the stadia rod and what is meant by reading it for a distance. So let's go all the way back to that circle. When you look through a level gun, you see these marks. You see a bullseye. The bullseye is where you want to be level. This is the spot you want to read if you want to read level. But it has 2 different hairs on it. They're upper and lower hair. The upper and lower hair are smaller marks, just the way this shows, and they're set to be at a multiplication factor of 100. So if you were to look at this and you were to see 1.5, you're reading 1.5 feet on that stadia rod, you look down here, and this one says 1.0, and this one up here says 2.0, you know that the person holding that stadia rod is 1 foot times 100 feet away from you. This is a very good thing to be able to do. You can get distances looking at a level gun. You don't need a tape, you don't need a steel tape, and you don't need a total station. This is pretty accurate, maybe not accurate for a building or sidewalks and things like that, but it's pretty accurate for doing cross sections or topography of say a landfill or a borrow pit, or even for something like like a mountain of dirt, like how much dirt is in the stockpile. So these are called reticle crosshairs, but it's what you're looking at inside the instrument. And here's a set of notes on figuring out the distances and what you're looking at and how far you're reading. So basically it's taking a top hair, a middle hair, and a bottom hair. This is called 3-wire leveling. And when you do that, you get these distances. You can read through the book and see how this works. You don't usually keep track of the distances that much. They can be done for cross sections, but the 3-wire leveling was also a technique for checking yourself and making sure what you read is in the right spot. This is, like I said, this is for a borrow pit. You know you're going to come in here. Let's say you're going to take gravel out. So what do? You get shots. You measure along a baseline. You turn 90 degrees off that baseline, and you take shots every 50 feet with your stadia rod. How do you know you're taking shots every 50 feet? You read the elevation in the stadia rod. You read those numbers, and you'll be 1.5 feet apart, and you take a reading. So that's, again, something very important. You can plot this, and you could be able to get the quantities of the work you're doing and how much gravel maybe is coming out of a hole. I did work like that for a landfill, actually, and it was to see how much would go in the hole. The Appeal landfill in Calvert was set up like that. We did some work that way. Here, people don't normally do this. You can. You want to know that distance. You can get a slope distance. You can read the angle on a slope, get this angle, and figure everything out. People don't usually do this. If you're going to go through that much effort, you're going to use a total station. And this is kind of interesting here. This tells you got a benchmark, and you're going to run all the way through here. You're going to set control around, say, a subdivision. You're going to build a new, let's say you're going to build a new subdivision, a new shopping mall. You run elevations, take your level, and you get shots all the way around here so that you can set all these other benchmarks, 201, 202, and 203. You think there's error, so you get a distance in between each one, and you run these levels, so you're keeping track. That is where the 3-wire leveling comes into play, and you keep track of your distances in between here. When you get back to the starting point, there's error. How do you fix that error? Well, it's right here. You use adjust the error based on distance. So when you find out right here is your total error, you're out 0.15 meters, it says. You want to distribute that based upon the length right here multiplied by, let's see, this is the distance, yeah. See how they're using the 4.7 was the total distance. Here's the leg in between, and it's a cumulative correction. So the further you go, the more error you have until you get back to the starting point and you're balanced out. Then you put new elevations on it. So that would be something that you might do. but a surveyor is going to be the one more likely to do this and to set that control over that big a distance. So that's all I have for chapter 4. It was a little bit more talking than I wanted to do, and believe me, you can always pause and take a break, because as times talking, I'd rather have to pause and take a break. But it's a lot of information to give you that is some of the most useful information in this class and in the textbook. So if you have any questions, be prepared to talk to me. Call me, email me. And again, on Mondays at 7 p.m., I will have the office hours for any questions that you may have. I won't be lecturing and teaching, but I will be answering any questions you have. And that's Mondays at 7 o'clock. So I will stop the recording and see you all next time at the office hours or at the next lecture.